Okay, hello everybody. So let's begin with the session. Welcome to yet another session of Summer School 2024. Till now, you would have learned how to build a robot in AutoCAD and all the mechanical and the electronic stuff. This is going to be our first session where we delve into the software involved in robotics. We will be looking into two important modules which govern the software in robotics, that is ROS2 and Gazebo. So let's begin. This session is presented by me and my teammate. I'm Astha and my teammate Arvind.
Hello guys.
So let's begin. So in today's session, we'll be looking into these topics. First, because this is the first session, let us look into why software is necessary and how it plays a crucial role in building a robot. Then we'll look into the two major softwares, ROS and Gazebo. We'll be looking into the terminologies in ROS. I'll also demonstrate two examples in order to acquaint you practically to what exactly ROS is. Then we'll be looking into URDF and Gazebo. So let's begin. So first, why software? So software is basically the heart of the robot. It helps in bringing the robot to life. Just putting in stuff together will not help the robot work. In order for it to carry out all these actions that we desire it to, we need to properly code the software. It helps to control the functionality and behavior of the robot. It dictates every action that the robot performs, from the basic movements to all the decision making processes it does. It acts as the brain of the robot as well. So now that we're clear why software is necessary for a robot, we start with one of the most important softwares that we use while building a robot, that is ROS. ROS is known as the robot operating system. Now, as the name suggests, it should be an operating system, but technically, no, it is not an operating system. It is a software which works on a pre-existing operating system known as Ubuntu. Nowadays, ROS 2 has evolved, which is working on Windows as well, but Linux is preferred. Now, what is ROS? ROS is an open source set of libraries and tools which helps the robot building process more easier. It has a set of pre-coded programs that work for a certain robot functionalities. We can use these programs directly and install them in our robots, or we can also create new programs. So this basically acts as a library where you have all the information that you require to build a robot. This has made the robot making process much more efficient and easier, and that is why this is widely used by most of the robot building software scientists. Moving ahead, now let us understand what ROS is and what it does through an intuitive approach. Like for us as humans, what we do, we have three major organs. First, we sense stuff. We have eyes to look at stuff and sense that. Then that information is sent to our brain, which acts upon it, thinks upon it, and then further sends it to the different parts of the body which act upon that. Similarly, in case of a robot, these functions are carried out by camera, computer, and actuator respectively, as you can see on the screen. So what the camera does is captures images of its surroundings, sends that to the computer, which is the thinking or the brain of the robot. The computer then processes that information and sends it to the different parts, that is the actuator, the different parts, let's say the hand, the leg of the robot, or any of such parts, which then act upon it. So this information that is being sent from the camera to the computer to the actuator, all this information is communicated by a middleware, that is ROS. So ROS in this case acts as a middleware which helps in communicating this information to different subsystems of the robot. So I hope the basic understanding of ROS is clear right now. Moving ahead, now we look at the most important terminologies that you need to know before you start with ROS. So the first important thing is node. Now, what is a node? Node are basically simple executable programs that you code in Python or C++ files. And then these carry out the basic functions of the robot. Let's say moving a hand. Moving the hand of the robot is one basic function, and you write a particular code for it in Python or C++ files. And this particular code is going to govern that particular action. So this is called a node. It helps in implementing complex algorithms. We'll further look into its understanding using an example as well. But right now, yes, it is a simple executable program in the form of C++ or a Python code. Coming to message. Now, as I said, that there must be a transfer of information between different nodes. As you can see here, the sense, think, act, all of these, that is the camera, computer, and the actuator, all of these act as act as particular nodes. Now, the information that is being transferred between the camera to the computer to the actuator. Now, this information which is being transferred is called a message. In simple words, it is basically the information that is transferred between one particular node to another particular node. Okay. Now, this information is being transferred through a particular pathway. More about this in the later part of the session. This particular pathway is known as the topic. It is basically a named channel through which we are transferring this information between two particular nodes. The next important thing is a package. Now, package is also, it is very crucial to understand packages. Now, what is packages? In layman words, package is a set of nodes. Packages are a set of nodes that perform a particular functionality. Let's say locomotion. Locomotion can be done by the hand of the robot, the leg of the robot, or the entire robot itself. So locomotion turns out to be a single package, and there are different nodes which can be a part of that package. Now let us look at this through a simple example here, which I've demonstrated. So as you can see, I have two packages here, perception and locomotion. Perception, as the name suggests, is going to handle what the robot sees or perceives. So this acts as one package. Locomotion, on the other hand, acts as another package which deals with the movement of the robot. Now, perception, for example, has two nodes within it, camera and GPS. Camera is responsible for taking images of the surroundings. GPS, on the other hand, as all of you might know, is responsible for dealing with the coordinates and the location stuff. So camera and GPS act as two nodes which have their independent coding in terms of Python or C++, as I've already mentioned. So perception is one package, and camera and GPS act as two nodes within that package. Similarly, locomotion, there might be one program which deals with the hand movement of the robot, and there might be one program which deals with moving the robot by a certain angle. So these two independent programs are known as nodes, which come under the package locomotion. Now, information has to be transferred from the perception package to the locomotion package. So let's say the information is being transferred from the camera node to a node which deals with the movement of the hand. Now this message will be transferred in form of an image file, right? Because camera is responsible for taking images. So the camera takes images of the surroundings and then transfers this information to the hand movement node. So this information that is being transferred in the form of an image file is known as a message, as you can see here. And the pathway through which it transfers is known as a topic. So let us now look at an example in ROS2. I'll be demonstrating this example. You can also, I have also already uploaded the help sheet. You can use the help sheet for the commands that you can uh, run in your respective devices. So I'll just, okay. So I've opened my terminal window here. Now the first program that I'll be showing you is the Talker basic Talker listener program. We'll be looking at the nodes, the topic, and we'll look at it through a graph that it demonstrates. So let's see. So first we need to run a particular node. In order to run a particular node, the command is ROS to run. And let's say the name of this is the name of the node. After writing this, we press tab and you can see we get something written here, these three things that are written here. Yes, so as I said, nodes are in the form of files like Python and C++ files. So this CPP suffix here that you see represents that it is a C++ coded file. However, the PY here represents that it is a Python coded file. We don't usually use this native thing, so it's you don't need to worry about it. So the node that we're running is a CPP, C++ node. So we write CPP and the name of the node, that is Talker. We press enter and you can see that this node is responsible for publishing Hello World. Now this is publishing Hello World 1, 2, 3 and so on. Until I kill the program, it keeps doing it. So this is one node which is publishing Hello World. Let me open another terminal window and open another node. So the basic command to run a node is ROS to run. Then same thing, CPP. This time I want to run the node listener. So the name of the node is listener. These, as I said, ROS2 already has a few installed nodes and programs. This is one of them. It's already pre-installed. I've not made it. And as you can see clearly, so the hello world that is being published here, as you can see 5354 is the hello world which is being received here at the same time. Okay, so this node is responsible for receiving the information. As you can see, it says I heard, and this node is responsible for publishing that information. Now let us look at it through a graph. So I just write RQT graph and press enter. It is going to show me this graph here. Okay, so let us look at it. It's basically easier to understand through this. So as you can see, there are two things here, talker and listener. These written in oval shaped figures. So these act as two nodes. So talker is one node and listener is the other node. The message that it is conveying is called hello world and the number. Okay, so that is the message it is conveying, and the arrow, as you can see, the direction of the arrow represents the direction of the message. So the message is going from talker to the listener, hence this direction of the arrow. This slash chatter, as you can see, is the name of the is the topic name or the name of the pathway through which this message is being transferred. So talker and listener, two nodes. Chatter is the topic and the message that is being transferred is called hello world. Hope that's clear to you. Let us kill the program. You can put Control C to kill the program and type in clear to clear your screen. I'll just close all of this and I'll demonstrate another program, which is turtle sim. Okay, so again, to run a node, I write ROS to run. Now, then I write turtle sim. So turtle sim here is a package which contains various different nodes. And here I want to run a particular node that is turtle sim. So ROS to run is your command to run a particular node. Turtle sim is the package which consists of different nodes, and turtle sim underscore node is the name of the particular node I want to run. I press enter, and as you can see, some blue screen opens here, which is the turtle sim with the turtle in the center. Okay, so this is the particular node I've run. I'll open a new terminal, run another node again. You can try this uh, simultaneously with me. ROS to run, turtle sim again, the name of the package, and turtle Okay, so this is the command I'm using. I press enter, and as you can see, there's something which has come here. Use arrow keys to move the turtle, as it says. So that's what I'm gonna do. Here the cursor should be here, and now let us just let me just press the upper key. As you can see, the turtle moves forward when I press the upper key. When I press the right key, it turns by a certain angle to the right. The down key moves back, left, move. You can see all this is happening. You can play with this program. This is a very quite basic program. Okay, so hope this is clear that what has happened here. Now, what is actually happening here? We'll look at it through the graph again. So this is what we do. Open the graph. So as you can see, we have a graph here. This is a much more complex graph than the one that we had learned seen earlier. So let's see what's happening here. Again, these are the two nodes, the teleop turtle node and the turtle sim node. This was the node that I run first, and this was the other node. And again, there is information being transferred. We'll look into it. So let us understand this graph. So the first node, that is the turtle sim node, which I opened. Now this node was responsible for opening the graphical user interface, as you can see this. So it was responsible for opening this blue screen. So this node basically deals with the graphical user interface of the turtle sim software. And this particular node, that is the teleop turtle, it enabled us to actually it enabled us to use the arrow keys in order to move the turtle. So this particular node, it deals with you inputting something through your keyboard. Okay, and in this case, as you can see, your this is your topic, particular topic. We'll look into these two arrows later. It's not much of use. So this is your this red arrow, as you can see, is your topic. Here the information is being transferred from the teleop turtle to the turtle sim node. How is that happening? The information here is in the form of, that is the message is in the form of the keyboard inputs that you do through the arrow keys, and that message is transferred from this teleop turtle node to the turtle sim node, which in turn causes a change in the graphical user interface. As you can see, you are using the arrow keys and then the turtle is moving. So there is, at the end, there is a certain change in the user interface of the turtle sim software. So the message that is in the form of your keyboard shortcut is being transferred from the this particular node to the turtle sim node, which is causing the change in the user interface. And this is the name of the topic, or the name of the pathway through which the information is being transferred. This is the direction as the arrow suggests. So these were the two programs which you can uh, demo carry out on your specific devices as well. So I'll be sharing my slides again to explain and go further. Okay, so hope it's visible now. So we looked into two examples in ROS 2. Any doubts till now, you can come up with your doubts related to the two particular programs that I showed. Okay, moving ahead. So now let us look at the modes of communication in ROS 2. So the other two arrows that you saw was somewhere had to deal with this. Okay. So there are
Astha?
three. Yes.
Astha, if possible, can you please explain how the turtle sim graph worked again?
Okay. I'll do that once again.
Thank you.
Okay. So let me open the graph once again. Okay. So as you can see, something else has come on the screen. This is because only one node is running at the moment. So I'll just close everything, open it again, run the node. Again, ROS2, run. Okay. So this has opened the graphical user interface. This particular node that I run here, as you can see, ROS2 run. TurtleSim is the package, and the TurtleSim node is the particular node that I run. So, which is responsible for opening the screen or the graphical user interface. Now, I will open another terminal window and run another node, again from the TurtleSim package. So this is the name of the other node that I'm running, that is Turtle Teleop key. It is again from the TurtleSim package. Now I run this. Now as you can see, it says reading from keyboard and use arrow keys to move the turtle. So this node is responsible for taking in keyboard inputs. So yeah, I use the arrow keys and this is what it does. Let us look at the graph now to understand this. All right. So this is the graph here. So again, as you can see, there are two nodes, turtle sim node and the teleop turtle node. The two nodes are always represented in the form of these oval figures, as you can see. The arrow represents the direction of the transfer of message, and the thing which is written on the arrow actually represents the uh, topic name. All right. So let us look at this. We will look into the feedback and the status part again as after we learn the modes of communication. All right. So Turtle Sim and Teleop Turtle are the two nodes. Now, TurtleSim node is specifically responsible for opening the TurtleSim window. That is, you saw the blue window that opened. It is specifically responsible for the graphical user interface. That is the TurtleSim, the blue window that opened. The Teleop Turtle node, on the other hand, is responsible for taking in the keyboard inputs that you enter. Okay, so it takes in the keyboard inputs, processes them, and sends that information to the TurtleSim node. The TurtleSim node receives that information and then causes a change in the interface, that is the turtle moves up, as you had clearly seen. So the information here is being received by the teleop turtle node as in the case of keyboard shortcuts. Turtle sim node, can you see that through this arrow here? You can see the direction of the message through this blue arrow. The name of the topic through the path, that is the pathway through which this information is being transferred, is this. As you can see, turtle 1 cmd well is the topic name. So the information, again to summarize it up, the information is being transferred from the teleop turtle node to the turtle sim node. What is the message or the information? It is in the form of the keyboard inputs, that is the arrow keys you do. And this is the topic through which this information is being transferred. We'll look into these two arrows, what it says, what is action, feedback, status, after we learn the modes of communication in ROS2. I hope it's clear now. Okay. So I'll share my screen. Okay. Hope my screen is visible. So we were looking at the modes of communication in ROS2. So there are three particular modes of communication. As I'd already said, ROS2 is responsible for communicating. It is basically acts as a middleware which communicates the information between different subsystems or different nodes. Now, how it does that is through three methods. Now we look into that. Okay. So the first method is the publisher subscriber method. So what is this? This is basically a transfer of data from one particular node to multiple nodes. Right now, the examples we had seen just involve two nodes. So this publisher subscriber method actually transfers information from one node to various other different nodes. So the node which transfers or receives the information is known as the publisher. For example, as you can see on the screen, if camera.py stands for a Python file, as I had already said. So camera.py is responsible for taking images of the surroundings. Now it has taken these images. Now it is going to transfer this information in the form of images to various different nodes which require it. So one of the node is detect_objects.py. Okay. So these nodes here which receive the information are known as subscribers. The node which publishes the information is known as the publisher, which receives the information is known as the subscriber. Now let's say camera.py took images, transferred images. It transferred those images to detect_object.py. Now detect_object.py, as the name suggests, is responsible for detecting objects that act as obstacles in the pathway of the robot. Okay, so in order to detect these objects, it actually requires a complete view of the surroundings. So obviously, the information that is published by camera.py is required by detect_objects.py. Not only that, it is also required by mapper.py. Now, what is mapper.py responsible for doing? It is responsible for mapping the exact location of the robot in the form of coordinates. So, again, as the images of the surroundings are again required by mapper.py. So as you can see in this example, one particular information is being required by different nodes at the same time. So the again to summarize, the node which takes in the information and provide the node which publishes the information is known as the publisher. It is responsible for giving the information or distributing the information to different other nodes. And the nodes which take in or absorb the information are known as the subscribers. This is the basic publisher subscriber method. More on this in the later part, that is gazebo. Moving ahead, one other mode of communication is the services. Now, this is, as you can see through from the diagram, this is a bit different. So what is happening here? This basically works on a request response system. Okay. So one particular node, survey.py, sends a particular request to another node asking it to do something. Okay. So it receives, so survey.py again receives an information, it has some information and it sends a request to another node, that is move camera.py, requesting it to do something. In this case, from the example, as you see, move camera.py, it might be uh, requesting to move the camera by a certain angle. So that is the request which is sent by one particular node to the other. Now the other node which has received this request, it acts upon it. And after it has completed processing the request, it then sends a response to another to the former node, telling it that yes, whatever the request you had sent, I have successfully completed it, and these are the uh, responses or the information that you had asked for. So a request is being sent, and that node then is processing that request, completing the request, and after that request is completed, it is again sending a response back to the former node. So this, as you can see, entire process is this mode type of communication is known as services. Hope it's clear. Moving ahead to the last and the most important mode of communication, which is action. Okay, so this is a more complex and this is actually being used more efficiently these days. We'll look into why it's more efficient right now. Let's see. So again, there are two nodes here. Uh, a similar thing happens as in case of services. one node sends a particular goal to the other node. So it sends an information to the other node, asking it, informing it about the goal which has to accomplish. So controller.py has received a certain information, has received a certain goal which it has to fulfill. Okay. So it takes in the goal, processes. So controller.py takes in the goal, processes the goal. One thing which works differently here is it after receiving the goal, it continuously sends a feedback to the former node, that is waypoint.py. Now, what is this feedback basically? So this feedback that is continuously sending, through this feedback, it is trying to give a continuous progress or the status of the goal. So it basically through this feedback, it shows how far from achieving the goal it is. Okay, and what is the status of the completion of the goal. So this is one major thing, that is sharing a continuous feedback, and it is because of this continuous feedback why this actions mode of communication is more efficient. Because let's say you have sent a goal, the node is processing the goal, but if you receive a continuous feedback as to what it is doing or at what point it has reached in achieving the goal, let's say you face an issue in between, it will be very much easier for you to debug the issue in this case. As in the case of services, as you can see, it sends a response in the end. It directly sends a response in the end after it has completed the request. Let's say there is some glitch in between and there is some issue and the request is not completely processed and you face an issue. It is very difficult for you to debug the issue in case of services. But in case of actions, because you are receiving a continuous feedback, so you are well aware of what is actually happening in this particular node, which makes the debugging process much more easier. So not only does it send a continuous feedback to the former node, but it after the goal has been completely achieved, it also sends a final result. So after the goal has been achieved, it sends a result in the form of images or any other form of a message. So this result acts as a proof that yes, the goal that you had asked me to complete has been successfully achieved. So this sends a goal, not then there is a continuous feedback. Not only is there a continuous feedback, but at the end there is also a final result which acts as a proof of the completion of the goal. So this was about the modes of communication, and I'll just okay. So I'll just uh, show you the RQT graph for turtle sim once again so that you understand the other arrows there. So let me just write RQT graph. Okay, so as you can see, there's nothing running, which means there are no nodes running right now. So we just close everything again. And I'll just run TurtleSim node, which opens the user interface, another terminal window. Just and another terminal window. I'll open the graph. So let us look at the graph here. As you can see, this one, this red arrow you can see is the topic which was responsible for the transfer of information. However, you can see there are two more arrows here which are being sent. So as you can see, there is action written here which shows the mode of communication, that is action, and then there is feedback written. So this particular arrow acts as a feedback that it is continuously sending to the other node. At the same time, as you can see, there is one more arrow which represents status. This represents basically the final result. Uh, uh, so the action here which is written actually shows the mode of communication. The feedback here shows that this arrow is responsible for the feedback and this is responsible for the final result, which was that that it publishes after the goal is complete. This is responsible for the continuous information that it is sending through the topic. Okay. So I hope this graph is completely clear now. What each of these arrow means, what these nodes mean, and along with the direction of the arrows. Okay. So this was it for ROS 2 from my side. Any doubts that you have, you can ask me. I'll be here to take up your doubts regarding the modes of communication or the basic terminologies or the graphs or the programs that we run. Any doubts you can ask me.
Mm. Yes, Rajashekar, I saw that you have raised your hand. Do you have?
Yes, any doubts? Okay. Okay, so yeah, Arvind, you can take over.
So, hello guys, I'll be taking this session forward. One query that I had received from a lot of people was that they hadn't installed Ubuntu or ROS2 and or are facing problems in running that. So there is a solution to this. It's this site called Construct. Simulates a ROS environment uh, through various projects called ROSjects. Can you just, I'll just present my screen right now and you, uh, yeah. Is it visible? Is the screen visible?
Yes, yes, it is.
Um, the site is app.theconstruct.ai. I'll just I'll first share it in the chat over here. You guys mm, can simultaneously work on it alongside. So now it's asking for a login, and if you don't have an account, you'll have to sign up. I have already created an account, so I'll just log in with my account. Now the thing with this is that you can create different ROSjects in order for the same. So I'll create a new ROSject, and over here we'll be using ROS2 Humble. So I'll be selecting that here, and then for a simulation, you can use various simulations over here, as you can see. For my use case, I'll create my own simulation, and for a title, let's just say sample workspace, sample project, and we can create the project. Now we can run this. So we'll just wait for this to load. At the same time, I'll just while this is currently loading, I'll just walk you people are through how to create a workspace and certain packages. A workspace is basically a place where you can keep all your packages for easier organization. So what we can do for that is first, yeah, I'll open the terminal over here, and we can now we can in order to create a workspace, we'll first have to create some folders. So there's this command called mkdir, which stands for making a directory. And right now it shows that I am uh, at the home slash acm directory, home slash username directory, as we can see over here. This is the home directory, and I'm currently located over here. So I'll create a directory called sample workspace. And if I enter over here, we can see that a directory called sample workspace has been created here. So now how do we, so we'll have to create another directory called src over here. So what we can do is we can navigate into that folder by using this command called cd, and the name of the directory in which we want to be in is sample workspace. And if we enter, now we are in the directory sample workspace. Now we want to create a directory called src. Once I create this, a folder would be created. Now we can move back. We can move up. Double dots means that we are moving down, up the hierarchy. Once we are moving deeper, now we are reaching the surface. Now we are back at the home directory. Now there's this command to build a workspace called callcon build. Now if we enter, I was hearing echo. Was there any problem over here? Alright. Yeah. So now we can see that on Qualcomm build there was a problem, like duplicate packages names were not supported. That is because we weren't in the workspace when we are building it. So we now have to navigate back to the workspace folder, which is called sample workspace, and now we can use Qualcomm build in order to build the whole workspace. Now we can see that there are no packages, and the same thing has been highlighted over here. Zero packages finished. Now we can see that there are three new directories along with src, and we can see that over here with the command called ls, which basically stands for list. Now I had shared a zip file containing all the packages we'll be using today. So now within that, if you guys are working simultaneously, we can use this package called py-pubsub. Now, and I feel that Visual Studio would be helpful for this case. No, kids, not now. So what you need to do is we just need to move this package into the src file of that of the sample workspace. So now we just move into the src file. Now we just paste the package over here. Now we have a package over here in the sample workspace. Now we can rebuild the workspace, and we can see that one package has been finished. Now, now in order to run files within the workspace, there's this command called ros2 run. Now we run the package name called underscore pub sub. It basically stands for publisher subscriber, the same thing which Astha was doing earlier. And we run uh, a file within that called talker. Now what this does is it basically publishes the message hello world along with the number. Now you can find that there is a problem called package so and so is not found. Now this is because sourced we haven't sourced our ROS setup files and the workspace setup files. So in order to source the ROS setup files, there's this command called source slash opt slash ROS slash the version which we are using, which is humble slash setup dot bash. Now after this, we'll also have to source the install file. Now we'll run the earlier command again. Now we can see whether it works. Now we can see that it's working, publishing hello world. Now we'll open a new window and run the other node, which is listener, ROS2 run package name. Now once again there we have that problem. So what we have to do is we once again have to source the uh, install file. Now we can see that as it is publishing the message called, let's say it's publishing hello world 77, it's simultaneously getting received by the subscriber node over here in the form I heard so and so. And if you open another window, we can get to know the the topic info about the topic. So like I'll open RQT's graph, and we have this slightly complicated graph. We do not need the debug, so this is the most important gist. You have two nodes: minimal publisher, minimal subscriber, which is a talker and listener, and they are publishing, and the message is getting published through the topic/topic. So in order, now I'll kill this command, and we can see about we can there is a way to get info about the topic using the command ros to um, in topic in yeah we the this shows this basically shows the type of the topic. In this case it is a string message which is being published, and the topic/topic is being published by one node which we saw earlier, which was publisher, and being subscribed by another node. It is being received by another node which is called listener or subscriber. So I can kill this. um, so that is it about how to create a workspace and a package over here. And now we can see that our ROS has been created. So you can implement the same things using the various options. We have a web shell option which basically opens the terminal. Can open multiple terminals with the same way, and you have a code editor which is on a which opens the place where you can type all your code over here. So let's say we want to create a package over here, and we just want to move this over here, and we can for an example we can just build the workspace over here. Now cd the workspace name over here is ros2 workspace. Now we can use colcon build in order to build the same. Yeah, and as you can see it has been done. Now I'll just run a sample code in order to check whether it's working. ros2 run py slash pubsub docker. Now once again that's the problem, so we have to source the install file. Now we can see that this is working as expected. So that's it for construction. Now I'll get back to the slides and show you about how visualizing a robot can be accomplished. Do you guys have any doubts about implementation in construction? If so, you can ask me right now. Okay, so I'll present this. Okay. Okay, there has been a doubt about showing the construct sim qualcon, so I'll do that again. So once what I'll do is I'll open the terminal over here. You can see that the package which we have where we have put the package in this workspace called ros2 slash underscore ws. So first we navigate to that workspace. Now we can see that we are currently in the our current location, current directory is ros2 underscore ws. Now we just use the command called qualcon build for the same. Um, oh, okay. I'm so sorry. I'm so sorry. Uh, um, so what we'll do is we navigate to the workspace and we use the command called qualcon build in order to build this workspace again. That's all that is required in order to do the same. You'll just have to move. You'll just have to create a package, and you'll have to create the packages, uh, add the required files, and then build the whole workspace. Do you have any further doubts? Um, okay, then I'll move. I'll move on. Is my screen visible? Is my screen visible? Can somebody please like confirm whether it's visible?
Yes, it is.
Um, so now the so now we are Asta has talked about the various modes of communication with ROS 2. So we can begin with Gazebo. Gazebo is not exactly the thing. It is more about visualization. Gazebo is just a tool for visualizing the robot in a computer. So now we start with visualization of a robot. How we accomplish that is through this format called a URDF. It stands for Unified Robot Description Format. This is a widely used XML format in robotics for describing robots. I'll be showing a sample URDF soon enough, so you can wait for that. This is written in XML, which is both human readable and machine readable. This basically describes the whole physical structure and properties of robots. If for example, if you think about a robot, let's say a simple three-wheeled robot like an auto, it has one front wheel and a back left wheel, back right wheel. So now some links which we'll think about are the body of the robot, then the left wheel, the right wheel, and the front wheel. Joints are basically connections between the links which allow them to move accordingly. Sensors are additional stuff that will add on top of the robot, and collision properties and visual properties are the things like materials, colors, etc. This allows to specify appearances, collision models, so that you can more accurately simulate this in the real world. So now some important tags in a URDF which we can see are the robot tag. This is the root element of URDF file, and conveys about the whole robot structure. After that, you have the link files, link tags. This, as I told, these specify the different types of the different parts of the robot, and this includes visual properties, the size, geometry, and so on, and inertial properties. Now, a visual tag comes within a link tag, which specifies the geometry, whether it is a cylinder, cuboid shape, box, or so on. It also specifies the materials and the colors. Now, the joint tags, it defines joints which connects two links in the robot structure. This allows for relative motion between them. It specifies the joint type and dynamics of the same. Now I'll show PDF so that you can better understand how it works, how it is structured. I hope my screen is visible to you people. Is it? Okay, it is. So now I'll show you a sample URDF like this one. This one is the URDF version of the robot that I just described. This has a base footprint which basically that specifies the origin, and then we have uh, a base link, a link called lidar which houses the sensor, the left wheel, the right wheel, and the caster wheel, which is basically the front wheel. And after this, we have joints over here with like base joints, base lidar joint, left wheel joint, and right wheel joint. These specify the parent links, the child links, the position where this is located, and the type of joint this can be. Suppose in this case, the type is a fixed joint. That means it cannot move. If it is continuous joint, it means that it can maybe rotate. It can be revolute or a sliding joint. Over here, if there is an axe, we can see that over here an axis tag has been added. This means that the joint is a revolute joint. And for sensors, we add in plugins like the ones below over here. So now I'll show you visualize this in a how to visualize this in RViz. Now I'll explain to you what is RViz. So now there are two different softwares in order to simulate and visualize the robot. They are RViz and Gazebo, which we'll be using primarily. RViz is a 3D visualization tool which visualizes sensor data such as cameras and joint states. Gazebo, on the other hand, it just shows a real world application. It just simulates as to how the robot would work, would be placed in a real world environment. So I'll first show you guys how RViz works. So once again, what I would need you guys to do is go to the packages, take this package over here, my package over here, this package called my package, and add it to your workspace. Add this to your workspace and then build it again. You'll always have to add it to the source directory of the workspace. Always do not add it directly to the workspace directory. So now we have done the same, and and we can build the workspace altogether. Now I can see that the build has been successful. Can I just get a confirmation as to whether my screen is visible? Okay, I'll take that as an yes. So now we have successfully built this package. So we'll learn a new command over here, which is in order to run the same. The ROS to launch. The difference between run and launch is basically that we this opens a launch file which allows for launching the various surfaces together. So launch now the package name my uh, slash package my package, and now the file name, the launch file that we would like to launch over here is this one, robot state publisher dot launch dot py. Now once yeah, I forgot this now. Now we can see that uh, the joint state publisher has been opened. Now what we'd like to do in another terminal is open rviz 2. Now over here we'll have to add certain displays. Over here we'll have to add the robot model in order to visualize the robot, and TF in order to show how the various points work, how the various joints work. So now the fixed frame you'd have to change it to the base link of your whole robot structure. If it is something like an arm, you'll have to keep it as the base. So in this case, the base frame is the base footprint. So I use that. Now we can see some transforms over here. In order to visualize the robot, we click down, and over here there's this thing called description topic, right? That's this option. That's the setting. Over here, we click this topic called robot description. Now we can see that our robot can be visualized over here. You can see the basic structure of a robot. As I showed over here, we can see that like the base footprint is basically this part, the origin. The base link is this box, this green box over here, which you can see on top. Lidar is the cylindrical thing on top of this. We have the left wheel and the right wheel, and the caster wheel is basically just a sphere which we can see in the front. So now in order to move this, what we can do is this joint state publisher graphical user interface. We can just move this slider around. Now as you can see that I'm moving this right, you can see that the left wheel is actually rotating anti-clockwise. Now as I'm moving this to the left, it reverses its direction and it's just rotating clockwise. So it can just so we can use RVs in order to visualize joint movements and the likes of it. Now there is another application of RVs which we'll be seeing in a different example in order to visualize, in order to gather sensor data and all. So and once again I'd like to take this time to also show you the RQT graph, which this will give you guys a lot of clarity as to how this whole thing is working. So now as we can see here, there are 1, 2 and 3 nodes over here which are currently happening right now, and the topics which are being used currently importantly are TF/TF, robot description and joint states. So now I'll just visually tell you how this works. So we have this node called robot state publisher. This publishes the data are called in the topic robot description, which is basically this thing, to this node, the joint state publisher GY. Now this publishes simultaneously publishes the messages like joint states through the topic joint states, which is basically showing about the status of the joint over here. And that same thing is being published again to the node robot state publisher. And once again we can see that the same, and it is a cycle. That is how we can see that as we are moving the joint state joints over here, it is rotating simultaneously. In order to visualize the and another cross to topic info slash joint states, we can see that this is happening right now. And in order to gain information about the joint states, we can use this command called echo. Now as we can see, it is continuously like updating the position over here. We can see that something called 1.4840, this is not these just show the names of the joints, and position is basically the angle. So I'll just move this slightly to the left. Now you can see that this is decreasing. Now I'll just move the right wheel joint. Now you can see that the one below 0.069 is also increasing simultaneously as we are moving this. So you can use this in order to like in order to gain info on how your joints are working. So now I'll end all these commands, and we can move to gazebo. Now gazebo on the other hand, it is for outdoor environments, and it simulates the physical interactions between robots and the environment. So in order to use the same, first I'll open a sample world over here. So we'll open terminal, and we can enter this command over here. This basically just opens a sample world of a seesaw. And note guys, this we are currently using gazebo 11 just for reference. So now we can see that a world has been created. This looks pretty planned, but this showcases physical interactions good enough. So we can move and pan around the whole thing. So now, we can see that there are various links over here. So now suppose I just want to move this base link over here to the, let's say, a slightly to the right. Let's see what will happen. Now it has started to tip. That is because the balance has now started to balance was more towards the right side due to more torque, and the same has been showcased. Now if I just move this forward, see that there's not much of an effect. Now we can see that now the whole seesaw has toppled. Now let me just say I'm moving this slightly to the right. Now there's not much of an effect because there is still not enough force in order to tilt the seesaw. Now if I just move this a bit more, we can see that now it is tilted towards the right. Hmm. Now there's also an option to apply torque and force, which I'll be showing in another example. So now what I would like you people to do is add the last package which I've shared called add the last package which I've shared, which is called which is called URDF example to your workspace. So I'll move it to this sample workspace source file and add it over here. Now once again we'll have to navigate to the workspace which we are using right now, sample slash workspace and colcon build. Now you can see that 3 packages have been finished, and we'll have to source the install files again. Hmm. So now I'll show. Now I'll just uh, sh- show the visualization in Gazebo. So the command for this is ROS to launch again. Now once again, as we are launching a launch file, we'll have to see which launch file are we using. So the launch file which we'll be using for Gazebo is the launch file called rsp underscore sim dot launch dot py. So we go to the packet. We first enter the package name urdf underscore example, and then the launch file which we want to launch rsp dot underscore sim dot launch dot py. Now you can see that this has launched successfully. Now this is just now this is just a simplified example of a robotic arm. This is the base link, slider link. This is the arm link which is fixed, and this is the camera link which can rotate around this place. So now what we can do for the same is, now I'll just now there's this option to apply torque on this, right? And once again, guys, if you're lost, you can interrupt me anytime and ask your doubts. Okay. So now back to Gazebo. I'll click on this, and I suppose I want to apply some amount of torque. Let's say I'll apply around 100 newtons of 100 newtons of force instead. Torque, I'll show you what happens when you apply torque as well. So now once I'm applying this force, we can see that this has started to move. Now clear. Now this basically means that this is stopping. Now suppose if I want to move this back, now I'll start applying the force. Now that this has stopped uh, because the net force now is 0. Now I'll apply force of minus 100 newton. Apply a force of minus 100 newton in order to move it backwards. Now that has started to move backwards, once it has moved a bit, now we'll just balance the force by applying 100 newtons of force. Now we can see that the robot has stopped. And we'll try applying, and if we apply torque, this shows the axis around which torque will be applied. In this case, it will not work because there are no joints in order to apply torque on. There are no rotational joints in the same. Like even if we try something, nothing much will happen, as we can see. So now I can stop applying everything. Now simultaneously I'll open another window and use RViz. This is where now suppose you want to see data from the camera. This is where RViz comes in handy. Open RViz 2, and now we have an empty map, right? So first we'll first add the robot model TFs, which is basically coordinate transforms. And transforms are basically the interactions in between joints. And we'll also add an additional thing called camera. Sorry, this is not the one. I'll remove this. We'll have to add this one by topic. Now, yeah, as I now we do not know which topic we are looking at. So I'll cancel and open the RQT graph so that we can together see which topic do we need for the camera data. So I'll open RQT graph. As you can see, this is incredibly complicated, right? uh, i'll just I'll just simplify this for you guys. So we have this gazebo ross joint state publisher, which publishes data to the topic joint states, and that message is published to the node robot state publisher, and it finally sends data to the topic called robot description. TF is basically just showing us as to how this shows us the interactions of the joints. So robot description over here is the node in which we'll get to say the whole movement of the whole structure of the robot. Now about this camera controller is the node which shows the data of the camera to these various topics. It transmits data to these various topics: points, image raw, camera info, and image raw again. So what we can do over here, we can now I'll just kill this command so that now that we know, in order to get the camera data, we'll have to we can use this topic called camera info. So we can see that. So now in order to first visualize the data, we'll first open this thing. In here, the base footprint is called world. Now we can see the coordinate transforms. Now over here in robot model, we'll just specify the topic. Now we can see the whole now we can see the whole data. Now we can see the whole structure of the robot on RViz. We can visualize the robot on RViz. Now we'll add another visualization. Now we click by topic, then move to image raw and camera. Now we can see that this displays an image from the camera with the visualized world rendered behind it. Now we'll click OK. Now over here you can see that we can now see the camera over here. I'm not sure whether it's visible all that much to you guys, but over here you can see the camera. We can see the output of the camera. Now for where is Gazebo? Yeah. Now I'll just keep this side by side so that you guys can see it better. Now that this is not that important, we can open that later. I will just show how we can see camera data. Now let's see. Suppose I'm applying a force right now. I just apply a force of 100 newtons, or let's say first we'll make it a bit slower. Keep it around 60 newtons. Now if I apply, now you can see that this is moving, and as you can see, the robot is slowly moving forward, and the same is being showcased in the camera. um, like this is the movement of the robot, and now the camera, now you can see that the green platform is not visible. Now suppose I just apply a force of 100 newtons, and now I'll move it backward. Now look at the camera part over here, bottom left. Now slowly we can yeah, just wait for a few minutes. Now you can start to see the green platform. Now I'll just increase the force which is being applied. And now we can see that it has moved back. Now it has stopped because there is a because this is fixed and it has its limits. Now we can start to see that this has moved forward, because like it's just like throwing a ball. If you throw a ball, and it suddenly stops. It starts coming back, and it bounces back, right? This is basically what's happening. This is more of a physics simulator which shows how the robot will work in a real world. Do you people have any doubts regarding this? um is anybody Do people have any doubts actually? Can you if you had understood, can you just please give a thumbs up at least, so that I can know whether I anything I told was um, anything I told was understood, um, okay, I'll take that. Okay. Yeah, I got this doubt about where we can find good resources to learn about Ross, Gazebo, and Darvis. Actually, the best place for this is the official documentation. That is incredibly difficult to understand, that it has a huge learning curve, but this is the best option that is there currently. Otherwise, there are these YouTube channels which I'll be updating in the chat box. They are called Robotics Backend, and the Construct, if I remember correctly. The same one which is using, and which from which we are using Construct Sim. So these two places would be great resources for you to learn about all these things: ROS2, Gazebo, and Arviz. And if you have any doubt right now regarding Gazebo and Arviz, you can ask me right now. You can type it in the chat as well if you're okay with it. Um. Okay, then I think we have we have reached the end of the we have almost completed what we have set out to do. So as an additional thing, I'll just show the URDF as to how the second one worked. This robotic arm, the structure of this in this example robot URDF Zacro. Now, Zacro over here, it's just a way to minimize the length of the XML file. It's like functions. We use functions in any programming language for more ease of so that we do not have to avoid redundancy. Right. The same thing Zacro accomplishes. So here we have this thing called arm length, and we have specified that this property has a value of 1. Now we can use that the same in let's say arm length. Now we are using the same thing in order to visualize where where the arm length is located. Arm length by 2, it basically means 1 by 2, and pi by 2 is basically 3.14, and the same thing has been repeated across both the link and the joint. Yeah. And in order to visualize the same thing in Gazebo, we'll also have to add Gazebo plugins. Like over here, I've added a camera link and Gazebo references. It basically shows the sensor type of the sensors you are using. In this case, a depth camera, and it shows and it shows various information about the sensor which you are using. Like this case format, RBG, and so on. And this is a depth camera which we are using. So these things, these are readily available in the internet, so you can use these. You can just copy paste these and modify them to the data which to the code which you are using currently. Um, so that's it from my side. Um, um, yeah, yeah. I think I'll give it back to Astha so that she can tell about a simulation called TurtleBot. Um,
Can you stop sharing, Harvey?
yeah, sorry.
Just give me a second.
One note: this will not TurtleBot will not be demonstrative. We'll just show you. We'll just tell you about what it does, and you guys, and we'll just leave it to you guys to explore it yourselves.
Okay, so I hope my screen is visible. So one major thing is TurtleBot 3. Okay, so I have already given the guide to install TurtleBot 3 in the sheet that has been shared, which has the prerequisites. So you can go through that. It actually works on ROS 2 and Gazebo itself. You need to pre-install Gazebo for it. And after you install TurtleBot 3, what it actually does is TurtleBot 3 is basically a web designed robot, okay, which is designed in Gazebo. You can code that robot using ROS2 and Python. Uh, you can code that using ROS2 and Python, and then you can actually see the robot move, and it does tasks in the Gazebo interface. So that is what is basically TurtleBot 3. You can install it using the procedure that has already been shared with you. I'll be also sharing a small code which you can try after installing, and that is like a to do for you all to just go and explore and just play with it. So I'll share a small code after the session which you can use after you've completed the installation, and you can just figure out and explore what you can do with TurtleBot 3. So that brings us to the end of the session. Thank you so much for joining in. If you guys have any doubts, we are free to answer them right now. You can ask us doubts related to the entire session, related to ROS2, related to Gazebo, any of it, we are here to answer. A lot of people asking about attendance. Yeah, the attendance has been taken. So if you guys have completely understood the session, can you guys just give a thumbs up so that we know?
Yeah. And if you have any doubts, feel free to reach out to us as well.
Yeah, so I can see one question popping up, that is ROS and ROS2. So ROS2 is basically an evolved version of ROS itself. So earlier ROS was you could use ROS only on the Linux or the Ubuntu software, as you can as I've demonstrated. But ROS2 gives the flexibility to be used on Windows and other operating systems as well. Also, one more thing is ROS2 has a larger open set of libraries, and you can also correlate ROS1 and ROS2. So let's say you have some program built in ROS1, and now because since ROS2 is being in the usage these days, what you can do is connect ROS1 and ROS2 to uh, kind of transfer your set of programs to ROS2 and then use them on a higher version of the platform. So it's advisable to use ROS2, and also it's advisable to use the Linux software because it's much more faster than Windows and allows much more flexibility.
Additionally, there are many libraries which haven't been implemented on Windows or even the WSL things like Windows Subsystem for Linux. It will be better if you guys use Linux, specifically Ubuntu in order to use ROS2.
Yes, any more doubts?
Oh, oh, okay, then I guess that brings us to the end of this session. Thank you so much for joining in, and I hope we'll be posting assignments by today and by today or tomorrow, and we hope that you guys will work towards it. Thank you.
Thank you so much.